Okay, so the stream seems to be working for both Facebook and YouTube. Now the YouTube link, I've just put in the chat.
So if people start complaining about the video quality, you can send them to the YouTube link, Liam and Chloe, because it's got a better streaming quality.
So I think the YouTube one has already started, has it?
Back.
Yes, no, Gabby?
I can just see Macquarie Uni Astronomical Observatory. I can't hear anything though.
Just mute it for the time being so nothing goes through. Okay, we're live.
Good evening, everyone, and thank you for joining us on this wonderful Friday evening. I would like to begin with an acknowledgement of country. I acknowledge the traditional custodians of the land on which we are gathered and pay my respects to their elders, both past and present. I would like to extend that respect to all Aboriginal and Torres Strait Islander people here today. We're all gathered here today from different places, so feel free to put it in the comment section where you come from. I'm Devika Kamath, and many of you might know me from the last 2 episodes of Macquarie Space Travel. And welcome to the 3rd episode of Macquarie Space Travel. In the last 2 episodes, we finished 2 very colorful journeys of our own Milky Way and also some neighboring galactic systems. If you missed these episodes, don't fret. You can catch these episodes in the recorded links, and these links are going to be in the comment section below. Tonight, we are at episode 3. 2 done, the 3rd one on. This episode's going to be about all things planets. If you're like me and you love our solar system, then this is where you should be Friday evening. Today, we're going to take advantage of the planetary positions in the sky. It's a wonderful month to observe the planets. And before we waltz away on a glorious trip around our solar system, I would like to remind all of you that the hashtag for today's episode and every Macquarie Space Travel episode is hashtag Macquarie Space Travels. So make sure you follow us and you also ask as many questions as you'd like in the comment section below. The team is going to be monitoring the comments, so I will definitely make sure we try and answer most of your questions as much as we can. The universe is full of planetary systems, but our solar system, it's kind of unique because it's the only planetary system that has life the way we know it. And today, to explore that planetary system, I have with us a really good friend of mine and a very cool astrophysicist, Dr. Ángel López-Sánchez. We're in a lockdown in Sydney. We can't go pub crawling, but what we can do is we can go planet hopping. How cool is that? A little bit about Ángel. Dr. Ángel López-Sánchez is an astronomer and a science communicator at the Australian Astronomical Optics and the Department of Physics and Astronomy at Macquarie University. He's a dear colleague of mine and also an expert in the study of how gas is converted into stars in galaxies and how this affects galaxy evolution and also the evolution of the universe. Not only that, he's a globally recognized science communicator with visibility all around the world. He is also a passionate amateur astronomer, and if we're lucky, we'll see a little bit of his astrophotography today. Ángel, hola, and bienvenido to episode 3. All things planets.
Muchas gracias, Devika. Thank you very much, Devika. I'm really thrilled to be with you and to explore the planets of our solar system with you and with everyone turning in tonight. We are going to visit nearby and distant world, but for a started, I think I'm going to ask Alan to show the one special image. And let's see if you can guess what it is.
Great. I can't wait. I love surprises. So bring it on. Okay,
that should be the image that Adam is showing with the 12 inches telescope at our Macquarie Observatory.
Okay.
And what are you seeing there?
So, well, it is a bit faint at the moment. Let's see. The object is only partially illuminated, and it has a face. You know, I can only see like half of the object, though a little bit blurred at the moment. But I have a feeling it's not the moon. It's our sister planet Venus, isn't it?
Yes, definitely. I knew I couldn't fool you, that's for sure. But that is a trick that I love to do when I show in the sky to different people, and the moon and Venus are more or less in the same part of the sky. And people are very surprised because they see, hey, it seems a moon, but it is not moon. It is actually our sister planet Venus that we are seeing through the telescope. However, in these planets that are closer to the sun than the Earth, we can see the faces the same way that we see the faces of the moon as the moon goes around the Earth. So
that's really pretty cool. This image that we saw was live, and the good thing is when you have processed images, you can really see pretty pictures, but also you can use processed images to understand features and details. And the one thing I know about Venus is that it's a planet full of extremes. Ángel, I'd like to know if you agree with me, and if yes, can you tell us a little bit more about these extremities of Venus? Maybe we can start with this processed image of Venus that we're looking at.
Yeah. That is a very interesting thing, because we have seen a moment ago the image live as we were taking it with the 12 inches telescope there at Macquarie University at Observatory. However, if we really want to get details in astronomy, always, as you have explained this very well in the 2 previous episodes, then we have to go and take many images, combine them together, and get a processed image. And that was the image that we are seeing now here. There it is. And that was taken some few weeks or so ago here from Macquarie Observatory using the 9.25 inches telescope. And we can see still the face very well in this processed image. But coming back to what you were asking me about the extremes in Venus, it is just really that, because it's very, we can think about, for example, what is the hottest place in the solar system, and of course not taking into account the sun. And you might think, okay, that should be Mercury because it is the closest to the sun, but it is not. It is Venus. So starting with that is just really a planet of extremes. So Venus, it is still a rocky planet. It is very similar to the Earth in size. It is only a bit smaller, 82% the mass of the Earth, but it has we have the thickest atmosphere in any rocky terrestrial planet. And that is, for example, a very nice image taken by the spacecraft Mariner 10 in February 1974. But we cannot see the surface of Venus from outside. The dense atmosphere of Venus that have 97% of carbon dioxide, only 3% of nitrogen, and that is the main constituent of the atmosphere here in the Earth, but have also traces of sulfur dioxide and sulfuric acid, making the Venus also the strongest greenhouse effect. So it is really an example of how things can go very, very wrong in a planet. But even though we have been able to take images in the surface of Venus, because in the year 1982, in the 1st of March, the Soviet probe Venera 13, Venera it is the name of Venus in Russian, was able to land and it was alive, let's say that way, for almost a bit more than 2 hours before it was destroyed by the heat and the pressure and the corrosive gases. So that is the image that we are seeing there. The top one, it is the image that was taken with this space lander. And we can already see that the colors are very different, because in the surface of Venus, the temperature is an average of 450 degrees, as I said, hottest at the average of any point in the temperature in Mercury, and the pressure in the surface is around 90 times that we found in the surface of the Earth, 95%, 90 times the ones that we find in the surface of the Earth. So the spacecraft Venera 13 was just destroyed in a couple of hours, and that was the only thing that we could get some few images in the surface of Venus.
Oh, interesting. I mean, sometimes, we tend to forget that there's other planets like ours, but then there's extremities like we're just talking about. For example, Venus is so cloudy that it traps over 90% of the heat. If you compare that with Earth, the clouds only account for about 25% of the heat that we have on our Earth. So we definitely don't want to get our greenhouse gases up, guys. We want to keep the amazing temperatures that we have on planet Earth. The other thing I remember even as a child was, looking at Venus and, thinking that, wow, it's such a bright star. And we often called Venus the evening star. But, as we've already heard, it's not a star. It's actually a planet. And that's the amazing things about planets. Planets don't twinkle, stars twinkle. And this is because planets don't burn their own gases. They actually have reflected light. And in fact, we call this an albedo. Angel, can you tell us something about Venus's albedo?
Well, it is actually the planet in the solar system with the largest albedo. Because around in number it is 0.76, meaning that 76% of the light is reflected by the clouds in Venus, which is quite interesting because that means also that a lot of radiation is going away, but infrared radiation is going through, and that is what is also doing the runaway greenhouse effect. That is, for example, if we compare the brightness of Venus with the brightness of the moon, you say, well, the moon is much, much brighter. But actually, the moon is quite dark. It is one of the darkest objects, not the darkest, but it is on the low part. So the Venus is reflecting almost 6 times the amount of light that, in proportion, the moon does. So it is quite bright, and it is so bright that when it is in some moments much closer to the Earth, and I have seen this, it can cast shadows if you are in the middle of the darkness. And I have seen that very nicely on top of the Anglo-Australian telescope, some beautiful dark nights. And you see your shadow only by Venus on the dome. That was amazing.
Fantastic. All right, there's so much to see, especially using our wonderful telescopes. Before that, I'm going to take a quick question. We have a question from Ronnie Law who asks, how does a planet get its color? Not sure if you want to answer that now or later, but...
Well, we can talk a bit about the colors. It's definitely going to depend on several factors. One, the amount of light that is reflecting, as we were talking, and the other is probably the main one will be the chemical composition that it has in the atmosphere or in the surface. Mars, for example, we see that it is very red because it has plenty of molecules that are with oxygen. And that is why they have this kind of iron with oxygen that is reflecting this kind of red light. Venus, we see white because of the clouds, but we will see later in Jupiter and Saturn that we have different colors, red, oranges, and so on. But because the different chemical elements that are there in the planet. It's a very good question.
Great. So maybe we should just go straight on and go to the next astrophysical part of the solar system. What do you think? Where are you going to take us?
Well, I think we have seen Venus already, and I tried to follow you being the moon. So let's go to the moon. Right.
Fantastic. Let's do the moon.
To go to the moon.
Perfect. Before we do that, I'd just like to remind all our viewers that, when we are doing planet hopping, star hopping, galaxy hopping, we like to use the tool that's called Stellarium. It is a tool that if you don't have a telescope, or even if you do, and you just want to locate an object in the sky, you can download Stellarium in your phone or your laptop, and you can use it as a free open source software to find the object you're looking for. So, Angel, take it away. Tell us all about moons and yeah.
Well, I also wanted to emphasize that Stellarium is absolutely great. It is a very interesting and good tool that you are using a lot, and many people are using them a lot. It is free software, so you can actually download it for any PC, Mac, iPad, tablet, or whatever, or even phone. There are many other apps that you still can use. There are some few that are very simple. The problem with Stellarium, perhaps it is a bit difficult at the beginning to be able for people who are starting to be able to use it. So I recommend one that is called Planets. That is very easy. It's only have the brightest stars and the main planets, the 8 planets, and you can select where they are. And they also have the virtual reality or augmented reality things that you are moving your phone to different parts of the sky and you're identifying the different constellations. I also like a lot Sky Safari, but Sky Safari has several versions and one is free and the other you have to pay for them. But in some way, very similar to Stellarium. So as I said, plenty of possibilities for there. But let's go to the moon.
Great, let's do it. We're going live.
There it is. Oh, that is a vision that everyone in every moment that we are using the telescope and look through the telescope to the sky and they see the moon, everyone is just completely wow. It's just really amazing. So this is an image that we are taking with the telescope, a refractor telescope. It is not having too much magnification because actually I always like to show the moon with taking all the full disk of the moon in order that we can see much better the differences between the day and the night, and also the contrast between the seas or the low areas of the moon, which are these dark gray areas, the basaltic areas, and the highlands of the moon that are heavily craterized. They have plenty of accident. When we say accident, geographical accident, craters, mountains, different terrains, and so on. In this image, that you can also see exactly what we call the terminator, which is the line where right now in the moon, the sun is rising, so it's breaking the day. And if you want to see shadows and you still really want to see the kind of 3D structure of the moon, and that is one of the things that people really love to do, then you have to go and move around that area because it is when you are going to have the highest shadows casted because the sun is low over the horizon, and that is giving you a fantastic view of an alien planet, which is our moon, located right now only 372,000 kilometers away, which is around 1.2 seconds in light time. So yes, it's really fantastic.
Wow, so this is now we're looking at a composite image of the moon that was taken by Ben. This shows so much detail, doesn't it?
Yes, indeed. It is just amazing. As I was saying, if you really want to get nice images in astronomy, you have to take many and process them. But still, here you see in this wide field image of the moon that is actually a composite emission, a mosaic with using the 9¼ inches telescope at Macquarie University. And you see the different very well the rays coming from the most recent craters and the sealands. You can even try to get colors. Actually, we can see colors in the moon if we do a bit of extra saturation. It's a bit tricky, but it can be done, and different positions. I forgot to mention it. I wanted to mention also a bit about the formation of the moon, because it is still there is still some debate, although it seems to be quite clear that we have a hypothesis about the formation of the moon that seems to have many evidences supporting that happened that way, that around 4.5 billion years ago, just when the planets were still forming and we didn't have an Earth, it was more a proto-Earth, but there were plenty of collisions around in the solar system, and a Mars-sized planet that was moving around the same orbit of the Earth And these Mars-sized planets have the name of Theia, which is the Greek Titan that was the mother of Selene, the goddess of the moon. Well, that small-sized planet collided with the proto-Earth. And then from the debris of the collision, we got the moon around the Earth. And plenty of things just to see around there.
Pretty cool. So basically these dark patches and the lighter patches, so this color density that you're seeing is actually physical gradients on the surface of the moon. So they're either the light patches are where you just have flattened soil after the impact, the craters have settled down, and then otherwise you're seeing craters, right? So that's kind of is that really the gradient that you see in the moon?
Yes, definitely, that it is. Because during all the solar system, the life of the solar system, there have been many collisions with all the planets, including with the Earth. And we know that very well. Well, we have the famous case of the collision of a big asteroid 65 million years ago, and well, that was the end of the dinosaurs. But there have been many other collisions, and we still observe collisions on our planet and collision on other planets. Well, at the beginning of the formation of the solar system, it was chaotic. There were collisions every day, many of them. And it seems that when the surface of the moon was more or less solid, it was not kind of magma well, at the beginning, and there were still some few big impacts that broke the surface, and from there the magma reappears on the surface of the moon, and that was what created the seas, what we see the dark parts of the moon right now, the dark patches, what we call the seas, for example, the seas of tranquility.
That's great. You know, in episode 1, I think we talked about wideband imaging versus narrowband imaging. So what we're seeing here are images taken using a wideband filter. I think we should zoom in and appreciate the magnificent details of the moon. And to do this, we might actually use another telescope, a 9.25 inch with a narrowband filter. Now, before we get there, I'd like to say that, as many of you know, for Macquarie Space Travels, in every episode, we have a big team working with us. The telescope team is, of course, led by the infamous Adam Joyce, who you will see one day, if you're lucky, and, of course, BJ, Benjamin Johnston. Tonight, we also have some of our AFA members behind the telescopes, one of whom is Andrew Kefella, a Macquarie University undergrad who is operating the 9.25. So maybe, Andrew, you could give us a sneak peek of what's happening at your end.
Thanks, Devika. Like Devika said, I'm operating our Celestron 9.25 inch telescope. It's a compact Schmidt-Cassegrain type telescope, which is about 24 centimeters in diameter and about 60 centimeters in length. Actually, it's this one behind me. It has the ability to magnify what we see between 100 and 600 times greater than our eyes can see. Mounted to the eyepiece is a color camera that is transmitting images to a computer at the university, which I'm remote controlling. Currently, I have it pointed towards the Sea of Tranquility on the moon, and it's here, just above this peninsula here, that Apollo 11 landed and Neil Armstrong and Buzz Aldrin took their first steps on the moon. But the image is a bit dark. So one of the things I can do to improve that is to increase the exposure. This is the amount of time that the telescope is collecting light per frame. And by increasing the exposure, I can increase the brightness a bit. And one of the other things I can do is increase the gain, which multiplies the signal that the camera chip is receiving. And here we've got a much brighter image, and it was just here, around here, that the Apollo 11 landings were.
That's great. Yeah. Angel, I know that you are very into mapping the moon and studying different parts. Would you like to tell us a little bit more about the part of the moon that we're seeing at the moment?
Well, we are seeing very clearly here in the middle, the dark part of the sea. It is the Mar Tranquility, the Sea of Tranquility, as Angie was mentioning. Just on the top, we start to see the Mare Serenitatis, or quite similar the name, I will say. It's not that easy to see, but there's some few bright craters there, like Manilus, almost in the center up. And then there are three that I love to see, but very close to the Mar Nectaris, which is the Mar that is bottom to the right of the Mar Tranquilities. And these are three very nice craters to see with an amateur telescope that are Theophilus, Cyrilla, and Catherina. And finally, the sea that we see at the right, that seems to be small, isolated, that is the Mar Crisium, the sea of the crisis in some way. Very, very, very nice. Yeah,
Right.
beautiful.
So, Angel, the moon is, one of the easiest objects to photograph. And I know that you have a passion for astrophotography, and you've taken some really cool images using your own telescope. Could you maybe show us some and tell us a little bit what you've done? Oh, that's wonderful. Who is that little one there? I think I know, but anyway.
Well, that is my son. That is my son, because you said that. So the moon is the easiest astronomical object to be able to take photos. You can do it even with the DSLR, with satellite lens. You can start to taking photos of the moon. Again, the trick is not taking one. The trick is taking at least 100. Some people are even taking thousands, are just taking a long video and then in some way processing them. That will be a very interesting seminar or talk just for explaining how we process these images and the planetary images in astronomy. That is different to the way we process, for example, galaxies and nebulas you were explaining in the previous episode. But I think particularly the moon, as it is that easy to get nice photos, particularly if you have a small telescope and you have the DSLR and you can connect it, even sometimes with the phone connected to the camera, to the eyepiece of the telescope, you can invite students and kids to take photos of the moon. And that was a project that I started with my son several years ago. Because he was actually taking the photos, I helped, pointed to the moon, of course, and prepared everything and did the focusing. But then, look, please go and click here, and you are taking your very own photos of the moon, and then later helping me processing those photos. So that was the very first photo that my son took of using this telescope. And later on, what we have been doing, it is taking images in different phases of the moon. Here it is a selection of only 8, but we have actually for all the lunations. Different phases, and we see how the shadows are changing, how the position of the terminator is also changing, how when the worst moment to see the moon is actually in full moon because you don't see very well the contrast with the crater. You see the rays from the most recent craters and nothing else. So yes, it has been really, really, really interesting to continue doing this project. And we have been doing that after all these years. And even the other thing that we can do, it is just taking images during a lunar eclipse. And that was the lunar eclipse that we enjoyed several months ago, on the 26th of May this year. And it is compiling perhaps around 150 independent images of a couple of seconds each, stacked together independently, the moon and the stars, and then I merged them in order that we could see this very red orange moon during the lunar eclipse and the background stars.
That's really great. And firstly, Luke surely has to be the youngest astrophotographer I know. And maybe we should get Luke on our show sometime. That would be really cool. He can teach us how he's taken these glorious images.
He will be happy. He will be happy to do that. He has been participating in a couple of the podcasts that I have released. So perhaps he will be keen to do it next time.
Okay, well, absolutely. We'll always welcome him on board. I'd like to say also here that, these beautiful images, including the ones we see on live today, and even this lovely red moon during a lunar eclipse, is basically looking at the one side of the moon, what we call as the near side of the moon, because the moon is tidally locked to the Earth. Tidal forces from the Earth have slowed the moon's rotation to the point where it's always the same side of the moon facing the Earth. So we call this tidal locking. The other face of the moon, which is almost never visible from the Earth, is what we call the far side of the moon.
Yes, but thanks to the space exploration, we have many images of the far side of the moon. The first images were taken in 1959. It was a long time ago. Again, by another Soviet probe, the Luna 3 or Lun 3. And yeah, that was really shocking, because we saw that the other part of the moon, the part that we don't see, the far side of the moon, is a bit different to the part that we see, because it doesn't have any clear big sea. Only a little region in this image taken by the Lunar Recognized Orbiter in between 2009 and 2011. It is actually a mosaic of images. But yes, later the Apollo 8 astronauts were the first people to actually see the far side of the moon. And yes, as we have plenty of other spacecraft, even the very recent Chang'e 4 that landed on the far side of the moon in 2019. The Chang'e 5 have also landed recently this year, some few months ago too. And then we have much more information now. And it will be a perfect place actually for building an astronomical observatory, and particularly a radio observatory.
Great. So just to make sure, we're understanding this correctly, the images taken off the far side of the moon are not because the far side of the moon ever faces the Earth. It's because we essentially have to go to the far side of the moon, right?
Exactly. Yes.
Okay.
Exactly.
Wonderful. I have some interesting questions coming through. The first question being, why are most of the objects in our solar system round?
Well, that is another excellent question, and I will say that actually that is not right. The majority of the objects in the solar system are not round. Only the bright planets, the planet and the dwarf planets, they are round. But the majority of the objects in the solar system are asteroids or comets that have very irregular shapes. And we have seen many of these with spacecraft and so on. But a planet is just rounded because of gravity. It's just that. And it is actually one of the conditions for being a planet or being a dwarf planet, that you have to, the object have to get what we call an hydrostatical equilibrium, in the sense that everything is just rounded and there is no significant peak or irregular shape. It is a clever question, but at the end, the answer is gravity, as in many other answers in astronomy.
Absolutely. I mean, one of the reasons Pluto is not a planet today, or was deemed as, not a planet, is because it was too small. It didn't qualify the size criteria, right? So for a planet, something has to be kind of round. It has to have cleared everything around its orbit, and it has to be at a particular size. So I think there's a few definitions on how something classifies as a planet. But I agree with you. I think not all objects in the solar system are round. It looks or appears that way. We have another interesting question, which I think you might have covered already, but I think it's a good question to ask. Because it's so obvious when you look at the surface of the moon. Matt Poole asks, because Xavier wants to know, how did craters form on the moon?
Okay, well, perhaps I should have been much more clear when I was talking a bit about that, but basically they are all impact craters. So it is just the collision of the many asteroids or meteoroids or small rocks that are around the solar system, and when they collide with a surface, they create craters. And that is a very interesting tool, because we can say how old a surface in the solar system is considering the number of craters or impact craters that we see in the surface. We know, for example, that some of the moon around Jupiter and Saturn, for example, Europa around Jupiter, we see that they don't have impact craters, meaning that the surface is very new. It's have been regenerated, and we know that because it is a very thick layer of ice and have some activity. So it is very interesting. So an object like the moon that we see plenty of craters, or Mercury is quite similar to the moon. And many people, if you put the photo, that is the other trick I like to do, but these are in presentations, put in a photo of Mercury and everyone is saying, oh, that is the moon. No, that is Mercury, because have many impact craters. In the Earth, we don't see many of these impact craters. We have identified 200, around 200, but the majority of them are later removed or erased because of water, oceans, sea accidents, the tectonic plates, definitely all the movement of the geological movement on the Earth, such as cleaning all those impact craters. But yes, the craters of the moon, all of them, have been created because of a collision of a little asteroid or big asteroid or a comet or something like that collided with the moon.
Great, thank you. Well, there's so much to see, but before we move on, Angel, it's not something I thought I'd say, but thank you for taking us to the moon and back. It is also one of my favorite songs, for those of you who know. Anyway, moving on. So, Adam, we are kind of having clouds with us at the moment, but we're going to try our best and showcase the best of what we can see with the solar system. That's Adam showing us a very cloudy kind of sky, but I
can't believe it. It has been clear all the day. We were so excited, and now in the last moment, these clouds are just...
Yes. But this is the life of an astronomer, right? We are always
the life of an optical astronomer, because in radio astronomy we actually don't, unless you are doing millimetric observation. But if you start doing standard radio observation, that you don't care about the clouds. But anyway,
absolutely. But anyway, onwards. How about we leave the solar system in terms of the terrestrial planets and try and study or look at others? Where are you going to take us next, Angel?
Well, the next one, it is clear. Let's go to Jupiter.
Wonderful. Let's do it. So the one thing to keep in mind is we've sort of looked at terrestrial planets, which is Mercury, Venus, Earth, and Mars. And now we're looking at Jupiter, which is a little bit different. And Angel's going to tell us a lot more about this striped planet.
Yes, because you were saying that perhaps we are sometimes identifying, perhaps because of science fiction, a planet like something solid, a terrestrial planet. And we only have 4 terrestrial planets in the solar system. We could say that we have 5 if we put the moon. Some people, and we know that we can put the moon not as a planet, but very similar to, because it could have been definitely an independent planet. And the way that we studied the moon is very similar to the way we study Mercury, Mars, or even Venus, and the way that it was impossible. But we are now moving into the gas giant like Jupiter. So everything that we are seeing in Jupiter is just floating in the sky. We are seeing the external layers of the atmosphere. It is just amazing. And Jupiter in particular, it is just, as I said, a gas giant. So it is 11.2 times the size of the Earth, although in volume, it will fit 1,300 planet Earth within it. It's quite big. And the composition...
That sounds pretty...
Yes, it is big. It is quite big. Still, we always say the proportion. So around 1,300 planets, Earth will fit inside Jupiter. Around 1,000 Jupiter will fit inside the Sun, to have the proportion right. But the composition in Jupiter is very different to the composition that we have on Earth, because it's basically hydrogen. 90% it is hydrogen, 10% helium, and the rest traces, small traces of other elements, particularly molecules, very easy molecules, as ammonia and methane. These two are really important for planetary in the gas giants and in the gas planets in general. The other interesting thing it is that the ultraviolet radiation impact in the surface, in the clouds of Jupiter, and depending on the different areas, it's going to make that the molecules are reacting, and that is why we have the colors in this particular case. Something else that we have to know about Jupiter, it is that has the fastest rotation in all the planets. So if we were there, our day will be only 9 hours and 55 minutes. So that is what it needs to complete a full rotation around its axis. And an interesting point, it is that as it needs almost 12 years, 11.9 years, to complete an orbit around the Sun, a year in Jupiter have 10,476 days.
That is quite, yeah, that's quite long to finish a year in Jupiter. You age slowly then. So what we're seeing now is essentially two live telescope views, two on-sky views. And one of it is the 9.25 inch that Andrew explained, and we have another one which is the 12 inch, and I think the 12 inch at the moment is being handled by our very own AFA administrator Gabby, who some of you might have known from episode 2. So maybe I would like to invite Gabby to tell us a little bit more about the 12 inch telescope that she is using before Ángel gives us some more interesting facts about the massive planet Jupiter. Gabby, can you let us in, please?
Sure. So, hi everyone, I'm Gabby and I'm controlling the 12-inch Meade, the LX200. So not to sort of be rude to Andrew's telescope, but mine's bigger and therefore better, and it lets in a little bit more light than his does. So my 12-inch diameter is basically a bigger light bucket for light to fall into. This telescope sits on one of the piers outside the observatory, just like the 9 1/4 does. And what we've got on here is a color camera, the ZWO ASI 462 MC. The C is for color, that's the important bit. And it also has a 2x Barlow on it. So Andrew was talking about the magnification of what the telescopes can see. Mine's a bit bigger. So it can, we can do a 472 magnification without the Barlow, but the Barlow on it is a 2x Barlow, which gives 944 times magnification. That's why Jupiter looks so big in my telescope and smaller in Andrew's. So one thing I want to show you here is the GUI that I'm using. It's very similar to Andrew's. It just looks different. I've got the same controls where I can put up the exposure, which I need to do because we're fighting some clouds, and make it brighter. And one thing I want to point out, which is very special that's happening right now, is that you can see, or it might be a bit hard to see, but there is the shadow of Io, which is one of Jupiter's Galileo moons, as it's transiting. So we should be able to see Io later tonight, but you can see the shadow of Io on Jupiter's surface as well.
That's amazing. What luck to have an Io transit whilst we're doing a live stream.
Yeah, actually Io, and now we are seeing that in Stellarium, Io is in front of the planet. If we were able to process that video, that image, then we will be able to recover Io. It is very difficult to see in the raw as we were seeing live, but the shadow was very clear and evident. So it was awesome to see that. In any case, I think that beside all these the shadows and the transit that I will tell you a bit more in a moment, the other thing that we see very clearly, it is the different structure that Jupiter has, because the atmosphere is divided into several bands or belts, that these are the dark areas, and some zones that are the light areas. And they are moving independently. So sometimes we see in time lapses how they're able to move in one direction, the other in the opposite direction. It is quite amazing. I also have to say that typical wind velocity is there in Jupiter. It is there 360 kilometers per second. And the other very interesting feature in Jupiter, it is the Great Red Spot, which is an anticyclone storm that have been observed at least since the early 19th century, perhaps even from the beginning of observing Jupiter with telescope. However, it is not visible right now. It will be visible later at around 9:30. Our local time it will start appearing. Remember that as Jupiter speeds, the rotation is so fast that it's just moving very quickly. You see Jupiter, and with a difference in an hour, you will see something very different.
Absolutely. And these bands as well, they change every time you are viewing Jupiter, whether it's at different hours of the night or different days, because the wind speeds are so high, the position of these bands and the densities of these bands are also changing, which is lovely because it really tells you that the planet is such an active planet, just like many others. But in the case of Jupiter, you actually get to really see it. We actually have a time-lapse video of Jupiter, don't we? Any chance we can see that?
There it is. See if it wants to go. Yeah, it's really amazing. It was taken just a few months or so ago, but I love it. First, because it is taken for how long? It is for several, almost all during all the night. So you are seeing the movement, the rotation of Jupiter, but also you are seeing the satellites moving around. And as I said, in the Great Red Spot, it is also there. You see very, very clearly some other structures here in the bands and so on. The shadows of the satellites over the planet, even two satellites, one very, very close together in relative proportion, and one of them casting the shadow on the other. It is just amazing. But there is something else that I like in this video, that is just showing, you go again to the video, please, that is that at the beginning it seems blurry because the quality of our atmosphere was not good, and later it is much better. That is something that we call the seeing. That is how good the quality of the atmosphere it is in a particular moment. And for observing planets, it is critical that we have very good seeing in order that we can see many more details. Seeing in some way it is how good are you able to resolve things in the sky. And Jupiter still, although it is big, still is very small when you see it through a telescope. Really, really small, much smaller, definitely much smaller than the moon. So you really need a very good quality of the atmosphere to see these kind of details. But it is an amazing time lapse. Really want to congratulate all of you for getting this.
Absolutely. Actually, talking about the seeing, if we can we have the view of the 9.25 and the 12-inch showing Jupiter, if that's possible? If it's not, it's all right. Just as a comparison between the two scopes, but if not, it's all right. But maybe we can get the 9.25 back, or the 12-inch. Okay, this is the 12-inch. So you can kind of see the difference between this live view of Jupiter compared to the time lapse that that we just saw, that was taken with a larger exposure. You can kind of see the image quality looking quite different, and indeed it is quite fantastic what you can do with a small telescope, like a 12-inch or a 9.25-inch or even a 16-inch.
Well, you just said that because it is amazing the techniques, how have they evolved lately, particularly in the last decade or so. And as Jupiter is very dynamic, the atmosphere, as you have explained very well, it's changing continuously. Observations that are made by amateur astronomers are critical sometimes to observe these changes. So here you have the vision with the two telescopes, with the 9.25 and the 12 inches. Yes, definitely. Very, very, very nice. That could be in some way, but smaller, what you will be able to see if you were looking through an eyepiece. It's quite that. It depends how well you have trained your eye to see more or less detail, but you will definitely see the main bands and the satellites, that's for sure. But if we go back to the contribution of amateur astronomers into the observation of Jupiter. This is a great example of the collaboration between professional astronomers and amateur astronomers. There are many. And you want another day, we can discuss many more. But that is particularly one that is, it's just doing plenty of things. For example, amateur astronomers were the very first people, not professional astronomers, that realized that Jupiter lost one of the main bands, the southern equatorial belt, that is where the GRC, the Great Red Spot, is usually located. And in 2010, that is what you are seeing there. It was later recovered, but it is still a mystery exactly what happened. And also in that image, it's an image that was obtained by Anthony Wesley from Broken Hill here in Australia. If you see in the right part of the planet, you see a little point, bright point, that is a flash of a fireball, of a collision of an object with Jupiter. And amateur astronomers are starting to get many of these. Not many, but they're getting some few of them. And even this week, on Tuesday, a Brazilian astronomer was able to report one of these fireballs, and now it has been seen independently by 5 or 6 amateur astronomers around the world. And that is also important in order that we can count how many collisions with Jupiter are happening with asteroids. Another very nice example is coming with those images that we see on the right-hand side that are have been taken by amateur astronomer Andy Caselli here from Sydney. A couple of years ago, the amateur astronomers were also the first to realize that there were some kind of turbulent clouds and red spikes around the great red spot. And you see the differences there just in several days, in how it was changing. So that was incredible. That is something that amateur astronomers can do.
Yeah, amazing. I think that, amateur astronomy is such a wealth of contribution to how we can appreciate and understand so many objects in space. But the Great Red Spot is kind of shrinking, isn't it?
Yes, it is. And some people are a bit scared that it might disappear. As I said before, we know, since we have had good telescopes and, well, not good telescope, but decent telescope, let's say that way, and periodic registrations of observation of Jupiter at the beginning of the 19th century, it have been there. But we have seen definitely that it have been shrinking during the last decades. At the beginning, perhaps I remember when I was a kid that I was learning, okay, the Great Red Spot have a size of 3 to 4 times the size of the Earth. Well, not anymore. Right now it has the size of around 1 and a bit size of the planet Earth. So it is really interesting. But these observations of the atmosphere of Jupiter, as I said, it is one of the most active collaboration between professional astronomers and amateur astronomers. And even the best images that are taken of Jupiter by amateur astronomers are later used by the Juno science team to select the areas that the Juno spacecraft, that is a spacecraft that is right now around Jupiter, observing mainly the magnetosphere and the gravity of Jupiter, but it also has a little camera, the Juno cam, and the flybys that are passing, the flybys very close to Jupiter, they are selecting where this camera is going to take the photos, considering the images that amateur astronomers are providing with the most interesting areas that seems to be changing. So it is just amazing that this collaboration is so active.
I have some really interesting questions online, but the one thing we'd like to take this is why is the Great Red Spot actually red?
Well, again, that is because of the little traces mainly on methane, and we will go there in a moment, that the methane molecule, when you get the ultraviolet radiation from the sun, has some few reactions there, and that is making the red color. It's not only that, there are some few other things that we are still completely not sure how all of this is happening, but it is what the observations are pointing at. And we can also say that because, as we will see in Saturn later, Saturn has a very similar structure, but the colors are very pale because Saturn is much, much, much distant from the sun than Jupiter, and the ultraviolet radiation is not that strong.
Absolutely. So I like the comment that Adam's put in here that says it's red because people keep commenting on it and it's embarrassed. So possibly a non-scientific one. But, we can use other filters to kind of see and study Jupiter. And in fact, the 12-inch that Gabby is using has a filter cycler. And we will try and look at Jupiter now using an IR filter. And the great thing about the IR filter is it's going to show us the same planet, but different aspects of it, and also the chemistry is going to pop out much more. So maybe if you have if we can, it would be great if we can look at Jupiter through the 12 inches IR filter. Okay, there it goes. Angel, what do you think about that?
Wow, really nice to see. You see now in infrared, I see not only the shadow, I think it's not a shadow, it is the satellite itself, or it's still the shadow. Anyway, no, it is I think it is a shadow. The planet, the satellite should be still in the middle, more or less. Io. But it is good, it is great, because when we're observing in the infrared, we can get better seeing because of the condition of the atmosphere, so we can get much more detail. The problem is that we need a bit of extra time processing, and we also need a camera that is good in the infrared in order that we can get the best of that image. And that is why it seems a bit not as good, but still it's quite good. You see the bands, you see the shadow, and I can still see or say that it is good, because if you compare this image with other images, for example, the image that I got some few years ago, 20 years ago, of Jupiter, using a professional telescope, one night that I have a bit of extra time while I was doing my PhD thesis, and I was a young and naive astronomer in the Canary Islands trying to understand the star formation in dwarf galaxies. But it was Jupiter there at the beginning of the night, and I thought, okay, I'm going to point to Jupiter before it is dark and going to get some few images with a 1.5 meter telescope. And that was the image I was able to get in the near infrared. It's a bit different to what we have seen before, but still. And what it was very surprised, particularly, was to see this red, very vivid red lines that are coming from the ammonia that is in Jupiter.
Pretty cool. In fact, Adam just reminded me that the image of Jupiter in our poster for episode 3 is essentially taken using an IR filter as well. So you can see the similarities between the one that Gabby showed us just some time ago, the one that Angel took from his PhD days, and the one in our amazing poster. Okay, well, there's so much more.
That is that is an example, very nice example, that when you process that image, you will get a very high quality with many details of Jupiter.
Absolutely. Okay, so let's keep going, because there's so much more to see. And I'd like to take the next stop in one of my favorite planets, Saturn. I think it's everyone's favorite. It's got a bunch of rings with cocktails of gases. So Angel, would you take us to Saturn and tell us a little bit more about the amazing planet?
Well, Saturn, definitely, it is the crown jewel of the solar system, or the Lord of the Rings. It is just magnificent. I will say, for me, well, sometimes it's difficult, but if I have to choose one of the planets, perhaps I would rather prefer Saturn or Jupiter, because everyone is, wow, we can see the rings. Yes, you can see the rings, even with a small amateur telescope, those that they are selling in the stores, the standard store, you can see the rings. It's just amazing. But Saturn is like Jupiter, it is a gas giant, although the chemical composition it is a bit different, because 97% is hydrogen and 3% helium. In Jupiter, it was 19% and 10%. And its size is around 9 times the size of the Earth, although the mass, it is only 95 times the mass of the Earth, because it has very low density. Perhaps our viewers and you have heard about that. If we were able to have Saturn in a giant ocean, it would float, because the density is lower than the density of water. But as I was also trying to say before, it has a kind of same structure in the atmosphere that we saw in Jupiter. It has belts and zones. However, as it is much more distant to the sun than Jupiter, the ultraviolet radiation is not as intense, and that is why we don't see those colors so clear. But definitely, the key thing about Saturn is just the rings. It's just amazing that with a small telescope you can see them, and even you can see the main gap between the two main parts of the rings. That is called the Cassini division. And I think we can see more or less here in the 12 inches image. I think I can see there the Cassini division, this dark gap in the rings. But also something that I love to see, that is the shadow of the planet in the rings that you see behind, and the shadow of the rings in the planet. With the scene, it's a bit tricky right now, but it is more or less there. So it's just really, really, really interesting, all of this.
So can we try and increase the saturation in maybe the 9.25 to see whether, how that changes the live view image? Maybe we get to see more features or satellites, unless we're super cloudy, but maybe let's give it a try. Why not?
Yes, because when we see the same way that, for example, Jupiter, the brightness of Saturn with respect to the satellite is quite big. So if we want to see an image, more or less detailed image of the planet, then we will miss the satellites. And the other way around, if we want to see the satellites, we have to increase exposition a lot, and then we are burning. That is what we see. We are burning Saturn. It's just too much. I don't see any.
So just for clarity, satellites are another terminology for moons. So we kind of call them together, satellites or moon. Okay, it's the same thing. So yeah, it's a bit hard to see here. But if you do have a telescope at home, and you can play around a little bit with the saturation to see how you can bring out the satellites for admiring them, or to have a look at them. Oh, there you can.
I can see that now.
Yes.
Perfect, because we see the brightest one that is at the right. That is Titan. Titan, it is larger than Mercury. It's just very big. It is one of the largest objects in the solar system. And the other three, if you can go back, there we have on the top, that will be, if I'm putting this right, Rhea. And then at the bottom left, that will be Dione. And on the bottom right, Tethys. If I'm doing it right, I think. At least.
Yes, that sounds about right. It looks, you can see all four of them in the same order that it came out in Stellarium, actually. So,
yes. For that,
fantastic.
software like Stellarium, it is great because it will be able to tell you exactly where the moons are in a particular moment, and you can identify the moons very quickly.
So we have a question which is along the lines of how many moons can a planet have? How come our planet Earth has only one moon? Jupiter has 4 Galilean moons and several 60 around-ish, 64, I think, other, in moons in total. Saturn, at the moment, you can see a handful. So what determines how many number of moons or satellites a planet can have?
Remember the answer I gave before about gravity? Well, the same thing, gravity. The more mass you have, the more likely that you will get more satellites. The Earth have the moon, and in some way, I didn't mention that before, in some way we can even consider the moon of the Earth as a double planet in some way, because the proportion of the moon with respect to the Earth is quite big. But giant planets like Jupiter or Saturn, they have 70, 80 that we know. Probably there will be more. There will be some of them that are big and evident, and they will be always there, and some few others that might be asteroids that are going to be with Jupiter or with Saturn during some time, during some few million years perhaps, and then will escape into the space. There even, actually that is also happening in the Earth. There is an asteroid, near-Earth asteroid, that it might actually be a kind of satellite with the Earth, but it is not clear yet about that. But it is tiny, it's small. Yeah, so if we go to a composite image of Saturn, there it is, we can see that much better. Because in that nice image that was taken some few weeks ago, we are seeing at the same time the Saturn with the rings and the Cassini division clearly, and the shadows, and even the structure of bands in the atmosphere of Saturn. And then we can count 5 of the brightest moons around Saturn.
That's amazing. Composite images always bring out so much of features as we see time and time again. So in terms of the rings, is there any way we can see them in more detail? Because I'm really interested to hear. I can never hear enough about Saturn's rings. I'm completely obsessed with them.
Well, the best way of the best images that we have of Saturn definitely are the images that the Cassini spacecraft have been taking during the many years that they have been there. But unfortunately, it was at the end, when was that? It was 3 or 4 years ago, I think it was 2017, that it was sent into the clouds of Saturn because it was run out of fuel, and just for not leaving that object there. But it took thousands of images. And I invite everyone to look to the webpage and examine and enjoy the great views of Saturn that the Cassini spacecraft provided. That is one example that you see perfectly well, the Cassini division in the middle, but there are hundreds of independent rings around Saturn. I also like in this image, beside the different perspective and also the shadow of the rings of the planets over the ring, I also like that we can see the hexagon, a very interesting feature that was discovered there in the north pole of Saturn, and it's have been interesting to try to reproduce that. Then, well, definitely the rings.
So the rings are made of ice and rock, and they are particularly bright when we observe them, for example, with another filter like a methane filter, because these rings are made of that chemical gas. So maybe we should try and get an image of Saturn with a methane filter. And we can do that using one of our telescopes if the weather is not too bad. It's not. And this is the 12-inch with a methane filter. That it is. Yeah.
It's just fantastic. Again, if we were able to process the image, we will see many more details, and we will see definitely the disk of Saturn. But it is evident that the rings of Saturn, as we said, mainly made of ice and a bit of rock, they have a large proportion also methane in the ice, and that is why it is we see very clearly with this special filter in the infrared, the methane filter. And something else that it's really nice to see, it is to observe Saturn in different years, because every year the orientation of the rings is changing. As we see in this slide, that is compiling 5 different images obtained with the telescope at Macquarie Observatory during the last 4 years. And definitely we see how the orientation of the rings with respect to us is slightly changing. So it was very open 4 years ago in 2017, and now in 2021 they're starting to be close together, and they're starting to be a bit less orientated. And that is because of the tilt of the rotation axis of Saturn with respect to the orbit around the Sun. And that is quite interesting, because that means that around, as Saturn needs around 27 years, if I remember properly, 29 years and a half to complete an orbit around the Sun. Every 14 years or so, the rings of Saturn really disappear from the Earth, because the rings of Saturn, although they are very spectacular and very long, very big, but they are extremely thin. So when the rings are edge on, we actually don't see them. The thickness of the rings, it is between 10 meters and 1 kilometer, depending on the area of the sun. That is nothing when you compare to the 280,000 kilometers, that is around 3/4 of the average distance between the Earth and the Moon, that all the rings have in longitude. So it is just amazing.
And these orientations are really important, because this is why planets have seasons, right? So the orientation of the planet with respect to the Sun and the tilt. So I find this really interesting, because seasons are just a lot of fun, and we're not the only planet that enjoys seasons.
Yeah, definitely. And that is very important, because at the end of the day, many times, and that is something that I say many times here in Australia, seasons in many of the planets have seasons and are defined by astronomy because of the relative position of the planet with respect to the Sun, and considering the tilt of the rotation axis. So for us in Australia, actually, the astronomical beginning of spring will happen on the 23rd of September, next Thursday. Astronomically talking, astronomical season, still we are in winter.
Yeah. Great. So we've seen terrestrial planets, we've seen gas giants like Jupiter and Saturn. There is one more type of planets in our solar system, one more class, the really cool ones. Angel, could you tell us about the last type, and maybe we can even visit one of them if we're lucky?
Sure. Well, we have, as you said, the terrestrial planets, we have the gas giants, and then we have the ice giants. Till the 1980s, all Jupiter, Saturn, Uranus, and Neptune were considered just gas planets, gas giants. Okay, they are made of gas. However, we have actually realized that they are different. Jupiter and Saturn are different than Uranus and Neptune. They are different kind of planets, and that is why we call these ice giants. Although they're still made of gas, hydrogen and helium, both Uranus and Neptune also have a large proportion of ice, that we kind of define this ice like volatile elements that have chemical compounds that have freezing points that are very, very, very low, around 100 Kelvin, around 100 degrees over the absolute zero. And these ice are mainly water, ammonia, and methane. You see, easy molecules at the end of the day. So that is the Stellarium view of Neptune. And hopefully we can see the live view of Neptune if we have it there ready. Although I can still tell you some few more things about Neptune meanwhile, because Neptune is the most distant planet. If we are not considering the dwarf planet Pluto or the other dwarf planets in the outskirts of the solar system that are Eris, Haumea, Makemake. Right now, it is at a distance of 4.3 billion kilometers. That is, we are seeing Neptune, and we are starting to see there, really nice, that fluffy blue ball. We are seeing that as it was 4 hours ago. Remember that looking into the stars, looking into the solar system even, we are looking in the past. Neptune has a size of around 3.9 planet Earth, but a mass of 17 times the mass of the Earth. But it is really nice to see. It is also there.
So, just like other planets, Neptune also, of course, has satellites. Now, it's quite difficult for us to resolve Neptune in a kind of resolution we would like, because, as you said, Angel, it's pretty far away. Of course, we're challenged by seeing, and our telescopes are powerful, but still, we are limited by the size of the telescopes we have. But it's quite amazing when you think that we're studying a really far away system like Neptune using, I think this one's just a 9.25 inch telescope. I think that's really amazing. Actually, we have a really nice video of Neptune taken using one of the telescopes in our observatory that shows the planets and the satellites. This was taken with lots of exposures put together, so like a series of them. Can we have a look at that, if that's around?
Yep, there it is. No, it is just, as I said, and you said also, it is amazing that still we can see this planet that is, I will repeat the number, 4.3 billion kilometers away from us. And it is, okay, it is big when you compare with the Earth, but it is not that big. It is only even less than 4 times the size of the Earth. But in this video, we could see that very well. This, yeah,
and you can kind of see Triton, I think, in this video. At least the last time I saw it.
Yeah.
There.
Yes, Triton, it is the brightest satellite and the largest satellite around Neptune. And it is another very interesting object. It seems quite similar to what we have seen in Pluto, by the way. And it might have been an object that was moving around Neptune or in that area, and that was captured by Neptune. And we think that because it's moving in a funny, different way to what we should expect. This is the formation of the of Uranus and of Neptune. But definitely we can see it with this kind of videos and with techniques.
So you can see it now in the 9 1/4.
Yeah.
Oh yeah, there it is. That's
absolutely
really.
I mean, it looks small, like a smidgen of light, but remember, it is very far away, and it is one of the brightest moons of Neptune, which normally you wouldn't be able to see. So this is quite great. Actually, can we also study a little bit more, maybe using an image from Voyager 2, which is one of the space probes that actually went around Neptune and gave us a lot of detail?
Well, that have been the only spacecraft that have been around Neptune, and that was the Voyager 2, that did the flyby of Neptune in August 1989. And I will never forget, because I was a teenager then, and I was excited about finally see what this beautiful blue planet looks like. And that image that we are seeing right now in August 1989 was in all news and in newspaper, and everyone was talking about that. And remember collecting that and putting it in my posters in there. But unfortunately, Voyager 2 only did this, the flyby. It was not staying around Neptune. Voyager 2 visited Jupiter, Saturn, Uranus, and finally Neptune, and every planet was pushing the Voyager 2 a bit faster in order that it was able to do these encounters. We are really missing a good space mission to study Uranus and Neptune. It is something that the astronomical community and people studying planets in particular have been saying for a lot of time. Because we still don't know many things about these beautiful planets. We know that they have also seasons. For example, we have seen the variation of the clouds. We see some few of the clouds. We also see in this image of Voyager 2 what it was named very similar to the greatest spot, but the dark spot. The great dark spot, and part of the blue color that we see comes actually from methane.
Right. Actually, I have a question that came, for Jupiter when we were discussing the great red spot of Jupiter, but I think it's a question that also applies to Neptune. And the question's asked by Rita Chung, and she asks, how do scientists measure the size of Jupiter or, Neptune and its red spot? In this case, for example, the spot on, Neptune. So how do scientists measure things that are so far away from the Earth, especially details like the size of the great red spot, or in this case, the blue dark spot?
Well, that is a very interesting question, and that goes just to the way we are analyzing data in astronomy. So we have the cameras that we are using. We know them very well. We know the resolution they have. We know the angular view that they have. And we know the pixel size. We know that a pixel size corresponds to this. And if we know the distance to this object, then we can measure directly the size of a particular area. Actually, there is a very nice exercise that I like to do with, I have even done it with high school students, to measure the sizes of the craters of the moon, or even the height of some mountains in the moons using the shadows, just using this technique. We know that this camera has this resolution, these properties, so we can take an image, measure how many pixels, how much is the distance, and with that, we estimate the sizes. So it's really, really, really cool.
That's great. And going back to, you said that the blue color comes from methane. I know that we have a spectrum taken of Neptune the other day. So maybe we can flash that up and you can tell us a little bit about what that spectrum gives us, and does that, match with the fact that there's a lot of methane that you see on Neptune. So here she is, the spectra. I love spectra. I just love spectra.
Well, we are astrophysicists. We love spectrum or spectra in general. I spend the majority of my work examining and studying different kind of spectra, and became being crazy trying to identify features, emission line, absorption lines. But it is a beautiful example, a beautiful spectrum. And let me try to describe quickly what we see here for people to understand a bit better. Because
and can you also tell us how you got the spectra? I mean, how did we get it? I think that would be very useful for all of us listening. So how did the process start, and how did we get it in the end?
Well, for taking the spectra, we use a little accessory that it is called a star analyzer, that is a diffraction grating in some way. So you have you see at the same time the object, that is Neptune, it is not seen here, and you see all the light that is dispersed, so in the different colors. When we say colors, in the quantity that in optical astronomy we quantify, it is in wavelength in angstroms. So that is what we are plotting in the horizontal axis. In the horizontal axis, it is the color, the wavelength. So in the blue color will be around 5,000, that is actually the green color, and the 8,000 will be the infrared color for us. We do not see that, the red part of the spectrum. And in the vertical axis, what we have, it is the amount of light that we see, the intensity of the light. If in codified in this light, in the spectrum of every astronomical object, there are always features that we can identify. And that is actually the key for us for understanding the distance to galaxies and to stars, the chemical composition. So we cannot go to a galaxy, for example, the galaxies that I observed that are 100 million light years away. We cannot go there and take a part of the galaxy and see the chemical composition. But with the light, thanks to these features, we can do that. We can analyze that light. And in particular, here in this spectrum, what I'm seeing, it is just these different 6 bands that are absorptions, that are features in absorption of methane. So we are actually seeing the methane that is giving the blue color of Neptune in this spectrum. And that is, again, something that even amateur astronomers are doing right now, because that is made, although it is made with our professional 16 inches telescope and Macquarie Observatory, even I have one of these accessories for getting a spectrum of stars. It is another very interesting thing to do. Perhaps another day we can talk about the spectra.
Yeah, spectra are like fingerprints. You know, we had a question before saying, how do we know that planets have methane or CO2 or any other gas? And that's because every element in the universe, whether it comes from a star or a planet, has a very unique fingerprint, just like we have fingerprints. And that's what you see in this spectra that Ángel and Adam have made together. These lines that you see, they are very specifically for one particular element, chemical element. And in this case, it's basically methane. And this is how planetologists and astronomers study what is the composition of the atmospheres around different planets, right? This is all so interesting. Now, we do have some questions, and they kind of span all through. One of the questions we have is, are there any other solar systems similar to ours that we know of? Do we have ice giants or gas giants in the universe, in stars, around stars like our sun?
Well, I love this question. The answer is no. We actually don't know any other solar system like the one we have now. And actually, it seems that our solar system is a kind of weird. And that is a long thing that we can talk a lot about all of this. Because even the very first exoplanets that we were finding, they were kind of Jupiter-like, but they were only orbiting their stars, the parent stars, in 3-4 days. They are called hot Jupiters. It is another kind of planet that we don't have in the solar system. In the same way, thanks to space missions like Kepler, and now with TESS, we are discovering many planets. Should have write down the number of exoplanets that we have now discovered, but there are more than 4,000 right now. And many of these are in the class between what we call the ice giants, like Uranus and Neptune, and the terrestrial planet that we have in our solar system, like the Earth, Mars, or Venus. They're in that inter the two categories, and we call them super Earth or mini Neptunes, because we actually don't know, many of them, if they are terrestrial planet or gas planet, ice giants, or ice planet, but with an atmosphere that is mainly an atmosphere. And it is very interesting because, again, another kind of planet that we have discovered that it is not in our solar system.
Yeah, pretty cool. This is a whole branch of astrophysics on its own, isn't it? Looking for especially Earth-like planets around sun-like stars. I mean, they sit in what we call as the habitable zone. Okay, great. We've done so much of planet stuff. Now, often I get asked this question, Ángel, and I'm sure you do too. And I'm going to get you to talk about the history because you're doing a fantastic job of it. And the question is around you have planets and then you have planetary nebula. In fact, I work a lot on planetary nebulae. The question is always along the lines of, are they related? Why are planetary nebulae called planetary nebulae? So maybe I'll let you explain to us the history behind planets versus planetary nebulae.
Yes, it is a very interesting story, because when astronomers were exploring the sky with the rudimentary telescopes, were starting to be better, but still not great. In the 18th century, they were starting to discover this kind of rounded nebulosities that they looked like a planet, but they were nebula. They were just gas, diffuse gas. And that is why someone put the name of planetary nebula. That is when the term was created. But really, in reality, it's just planetary nebula do not have anything to do with planets. And we are going to look at one of them. Actually, we have it already there. It is the Helix Nebula, which is actually one of my favorite planetary nebula in the sky.
Sure, I must just say that it is a bit cloudy, and that's, Adam, you read my mind. So you can see that we are pretty much clouded out. So it's going to be a little bit hard to get the Helix Nebula on sky. And the reason being, planets are still close by, but Helix is still quite kind of far away. So what we might do is, here we've got a beautiful image of the Helix Nebula. And maybe you can tell us a little bit using this the image we took some time ago. Adam, can you remind me as to which telescope this comes from?
It's a 9 1/4.
The 9 1/4. That's it. Yeah, thank you.
Yes, these are beautiful color images of the Helix Nebula. It is in the constellation of Aquarius, and it is one of the closest planetary nebula to Earth. It is at around 655 light years. That is a recent number of distances, because really knowing distances in astronomy, it is quite tricky and difficult and challenging, although it is critical, because we need to know where the things are in the space for deriving the proper physical properties. But the Gaia mission was able to estimate very well that the distance was around that 655. I also like to name it some people like the Eye of God or the Eye of Sauron, because of the structure that it has. And I also love to see these particularly color images, because they are also telling us the different chemical composition that is coming and the different physical properties that are happening in the planetary nebula, that you see very well this green blue color in the center, because very rich oxygen and also very high temperature physical conditions, and then the H alpha, the hydrogen, and the nitrogen in red color in the stellar layers. Remember that it's a bubble. We see the projection in the sky, so that is why we see it like an annulus, like a ring, but it is in some way a bubble, because it is the course, so the way that solar-like stars are dying. And well, here it is one of my favorite images that I took from my backyard here in Sydney, using my own telescope and dedicated H alpha filter. I think I combining around 6 hours of data, if I remember well, combining all together. And we see not only the ring structure with several substructures, but also some layers in the outskirts of the Helix Nebula that are consequence of the star losing some previous ejections of matter. And all of that have a radius of around 2.5 light years from the center of where the white dwarf star is located.
Yeah, this is amazing. And what we're seeing here is essentially the star that is kind of, dying, or, it's almost dead, and it's ejecting its material away in this nebula. And that's kind of why it's called a nebula. It's basically, a cloud of gas and dust. Now, one thing is we're looking here at a planetary nebula, which is a dying star, But there's another kind of nebula, which is essentially where stars are formed, called, they're called star-forming regions, or they're also called nebulas. So a nebula is a kind of a wide term that we use quite, commonly in astronomy and astrophysics, indicating lots of gas. And this image that you've taken, Ángel, really shows different layers of that gas, because that wind, the stellar wind rather, has a velocity, doesn't it? And it's kind of moving away from the dying star.
Yes, that is also one of the reasons why I like these kind of structures. And yes, they are really, really beautiful. What will happen to the sun in how much? 4.5, 5 billion years from now?
Yeah, actually, you know what? Yeah, there's so much we can learn, and some of it we've seen in episode 1 and 2. Nebulas have so much of information in them, and you've just probably given me an idea for what we might do in the next episode. And here's another fantastic star-forming region that we have popped up. But I'm not going to steal the thunder, and I know exactly the person to bring for the next episode to tell us a lot about nebulas in the universe. But before we are reaching a close of episode 3, but Ángel, there's so many questions online, and I'd like to ask you quite a few of them. So one of the questions I have, and it's a really interesting one, which is, what is the source of the internal heat for Jupiter and Saturn? Does it have a source of internal heat?
Well, actually, they have. And in Jupiter in particular emits a lot of radiation in infrared that is not coming from the sun. It is coming from internal heat, plenty of heat. Saturn too, but particularly Jupiter. When you see in other wavelength in infrared, long infrared, is just amazing, or even in radio too. But that is because of the atmosphere, the magnetic field that also Jupiter has. So yes, definitely, it's still have plenty of that emission.
Yeah, I mean, we have a question that's just popped up, which is it's from Harry, and Harry asks, why do stars die? I think it relates to the dying stars that I mentioned, but I'm happy to let you take it. So, Ángel, why do stars die?
Because nothing lasts forever.
Like this episode, which is also kind of coming to an end.
Let me give a bit of extra, but not much. So remember that at the end of the day, a star is just a giant ball of gas, mainly hydrogen, and in the center of the star, hydrogen is fusioning together, forming helium. That is also why I like to say that the stars are like cosmic kitchen, because you put something and you are creating new elements. It's cooking. But there is a moment in which that hydrogen is just empty. It's just cannot process more, and then something is happening to the star, and depending on the mass of the star, it will process more elements, helium into carbon, oxygen, and so on, perhaps getting into the iron, and then it will explode as a supernova. Or it will happen like we have seen in the helix, and it will happen to our sun, that definitely is just, there is not enough gravity, and the external layers of the atmosphere just will go away, because they have been a red giant star, and it will go away, and then the center, the core, will collapse and form a dwarf, white dwarf star, and that will be the death of that particular star. But yeah, nothing lasts forever. Even the stars, for us, they are almost eternal, but the sun was born 4.8 billion years ago. It is now in the mid ages, and it will die in 4.5.
It's a teenager at the moment. Okay, so one last profound question, I think, and we will wrap up this episode. How is our solar system formed?
Oh, that is another very interesting question. Well, there is a long history, and there's several hypotheses to try to explain how the solar system was formed. But right now, the common idea, it is what we call the primigenic nebula, the common nebula of gas that condenses, and then from that condensation we form the sun, and around the sun, the disk was forming slowly the planets. And there are many different scenarios explaining that and trying to resolve all the questions for exactly how the planets have been formed. And it is very interesting. It is and still a very intense study topic for a study. And something that we have been known recently is that the orbits of the planets actually have been changing during the life of the solar system. For example, Uranus and Neptune were created much closer to the Sun, probably around where between Jupiter and Saturn, where they're now. And Neptune was even closer to the Sun than Uranus. But during the formation of the solar system, they were moved away. They migrated, that is the word that is used, for going into the external part of the solar system. So yes, but at the end it is just that we are coming from a giant cloud of gas that's condensed, forming the densest part in the center, the Sun, and then also for condensation and accretion disk. And the main bubbles, the main things merged together, forming little rocks, the planetesimal, forming later the planets.
Fantastic. Ángel, thank you so much for taking us planet hopping and, giving us an insight into the solar system, especially for all us Sydney-siders who are a little cooped up at home. A Friday evening planet hopping couldn't have been better than that. So thank you very much. And it was a pleasure. And we've all learned so much from you in this last hour and a half-ish.
Thank you. Thank you very much for having me. It is great, and I enjoyed it a lot, and I love to share the passion that I have for astronomy and for space, for planet with all of you. And I will be very happy to return and to be in another episode with all of you. Thank you for having me.
Absolutely. We will have you back in no time. Before we close, I would like to take a moment to thank the wonderful team at the AFA. And this is mostly made up of students, as many of you know, and we've spoken about before. Without the help of all these students, these episodes would essentially not have been made possible. So thank you very much to the whole team. We have a team with the telescopes. We've had a team helping us with the social media. We've had a team helping me host this particular episode and others. So this is a joint effort. So thank you very much to everyone involved. I also want to say that the Macquarie Observatory is essentially going to be open once the lockdown is lifted, and we will have this information on our website. The wonderful images we are showing you is just the tip of the iceberg of what we have to offer at Macquarie Astronomical Observatory. We often have school visits where school kids can come and spend an entire day with us. We have chances to take them through our labs, through the observatory, and even a pop-up planetarium where we get to kind of, observe the sky together. We also have the option where we actually take the planetarium to different schools on request. And of course, once the lockdown is lifted and following the COVID rules, we will be able to have people inside the inside the observatory, and the 9-inch and the 12.5-inch, you can actually observe the night sky with these telescopes. So when you do get the chance, and definitely subscribe to our AFA page and follow us on social media, so you are going to be the first to be updated when the observatory is open. So we will be back in a couple of weeks to take you through another fantastic interstellar journey. And until then, I wish you all a wonderful weekend, and space is for everyone. So go and get some space. Good night, everybody.